So today I want to talk about a general and very useful data structure technique called persistence. But first I'd like to motivate it with an application. And as usual, we'll sort of state what we want first out of the data structure, and then come up with better and better solutions as we go along. But first, the application. So the application is what's called next element search, or sometimes called point location. So what you want to do is you're given n non-intersecting line segments. And you want to build a data structure so that when you query some point P, you should return the line segment directly above P. If there is one. Otherwise, you can return null or none or something. So here are my n line segments labeled A through G. And if I were to query with this point P, then you can imagine shooting a ray upwards until it hits the first line segment. And then the answer to that query would be F, the segment called F. And if you give me this point P for a query, the answer is B. Okay. So that's the next element search problem. And it's also called point location for a good reason. So all I said is that these segments are they're non-intersecting, meaning two segments don't cross each other. In this picture, I happen to draw them all horizontally, but that's not necessary. The important thing is that they don't cross each other. And if you think about that for a while, well, you can get a lot more interesting sets of segments than like this, for example. For instance, if I give you a picture of a map, like so, then the boundaries of the cities or the countries in this map typically represented as polygonal chains, so just sequences of line segments. None of them intersect each other. Maybe they meet at endpoints, but that's no big deal. And of course, you know, it's important for all kinds of reasons to say for some location, which city is it in, or which country is it in, or if this is at a finer level of detail, you know, whose property am I on in the city of Ottawa right now? And you can do that by taking this map and simply labeling the bottom sides of each edge with the name of the country that's beneath it. So, for instance, if I do a next element search in this set of segments and it hits one of these three, the answer is one of these three things, then I know I'm in whatever, country E. So it's not just restricted to finding some particular line segment, but if you group those segments and label them appropriately, it will tell you things like which of these polygons your point is contained. Okay. So, question is, well, how do we solve this? And as usual, this is a static data structure problem. So we're interested in sort of three things. How long does it take to build the data structure? How big is the data structure? And how fast are the queries? Or how slow are the queries? All right. So one way to do this that is helpful for what we're going to study today is through the technique of what's called plane sweep. So what you do is you imagine taking a vertical line that starts off at infinity, like I'm going to disappear from the camera because I'm standing at infinity right now. And you sweep that vertical line segment left to right, and you take a little pause every time you encounter an endpoint of one of these segments. So let's see here. We start with a vertical line segment. The first thing it hits is the left endpoint of A. So we'll take a little pause there. The next thing it hits is the left endpoint of B. So we'll take a pause there. D. Then E. It was close, but C comes next. Next is the right endpoint of E, the right endpoint of B, F, G, and then we finish up with these remaining right endpoints. So once I've done that, I have a funny looking picture that these vertical lines that I've drawn now, they split my board or the plane into vertical strips. And if I look inside one of those strips, nothing interesting happens. In particular, there's no endpoint or there's no segment that begins or ends inside a strip. They all begin or end on the boundary of these things. So this gives me some divide and conquer strategy, a really naive one, that says, well, I'll do this. I'll split things up into strips. And then if I look at a strip, well, what's the next element search problem once I've figured out which strip I'm in? Well, everything is every segment either doesn't touch the strip at all, or it completely crosses it. So really, it doesn't matter that these are segments anymore. You can just think of them as lines, or you can even think of them just as some objects that are in some sorted order from top to bottom. And what I'm trying to figure out when I do one of these queries is, where does this point fit into that order? So here it comes, let's say, just before this segment F. But if it were here, it would be just before this segment A. Now, that sort of thing is kind of something we know how to do well, right? This is just a bunch of things that I can sort perfectly, just the parts restricted to one segment. So I can do something like put these in a sorted array or a binary search tree, and so once I've figured out which strip I'm in, I can just search in that sorted array or binary search tree to locate this point. And well, how do I figure out which strip I'm in? Well, the strips are vertical things separated by these lines. So there's an obvious order on those. Here's the first one, second one, third one, fourth one, and so on. And to find out which one I'm in, which one my point is in, I only have to look at the x coordinate of the point, and that will tell me, right? So if I just keep these strips in, let's say, an array in sorted order, then I can do binary search to figure out which strip I'm in. And then if there's a data structure that stores these items, then I can search in that data structure to find out which of these things the point is directly below. Okay. That makes sense? So if you don't worry about efficiency now, it sounds like we have a data structure. So if I have n line segments, I get something like 2n plus 1 vertical strips. Let's say store their x coordinates, like the x coordinates of the boundaries in a sorted array, maybe. And for each strip, let's call them S1 or S0 to S2n. And for each strip, Si, store the subset of segments that cross Si, sorted from top to bottom. Okay. So I think it's clear that the strips naturally go left to right, and as long as no two segments cross each other, then sorted from top to bottom has a natural meaning, even if they're not all horizontal like this. All right.
Pat,
Yes?
how will there be 2n plus 1 vertical strips?
Because there are 2n endpoints to the segments. Each segment has 2n, or each segment has 2 endpoints, and there's n segments. And there's a strip that comes before the first endpoint. Then there are n minus 1 strips that have 2 sides, and then there's one more that has only 1 side. So in general, if I take 2n numbers, they partition the real line up into 2n plus 1 intervals. Don't forget the infinite intervals attached to either end.
Does that mean the 1 is like the boundary?
Well, so this is, in the labeling that I've been using, S0 is here, S1, S2, S3, and then this is S2n.
Okay.
S2n is that, everything after this. Okay. But the exact number is not critical anyway. Sorted array with about a constant times n elements. And so that we should be able to search in O of log n time. And in a strip, we're storing the subset of segments that cross the strip in sorted order in, let's say, an array or our favorite kind of binary search tree, maybe a treap, in sorted order. And well, I don't know exactly how many intersect a strip, but I know that it is not more than n. And so there's at most n things that intersect this strip. So we can search for that in O of log n time. So what we're doing is just 2 binary searches, one on the x coordinate of the point to find the strip we need, and then one on the y coordinate to find the segment directly above it. All right. So this is the naive thing. And we're going to keep track of how well we're doing. This one does well with the query time. It's O of log n. But it also needs to know about space and construction time. So space, how big does this data structure get? Well, this is where it doesn't do so well. At least if you give me some bad line segments, it's not going to do well. In particular, if you give me a set of line segments that looks, say, like this, then that gives me a bunch of strips where S0, well, it has 0 segments crossing it, but S1, that's this one, has 1 segment crossing it. So let's keep track of that. S2 has 2 segments crossing it. S3 has 3 segments crossing it. And at least in this, for this collection of strips, where every one of them starts before any of them end, so all of the left endpoints appear before any of the right endpoints, then by the time I get to strip Sn, that is this one, it has n segments crossing. And if all I'm going to do is store those things, each one is going to, this is going to be, let's say, in an array of size 1, an array of size 2, an array of size 3, 4, and so on. Well, if I add all that up, this works out to n times n plus 1 over 2. The exact number is not important. The important thing is that there's an n times n in there. So this is quadratic space, n squared space. So that is, I'm going to say, well, theta n squared with a little star. That means, star means in the worst case. So I just, this argument here just showed that it can be, at least n squared, and it's also at most n squared, because in the end, it still is only 2n plus 1 strips. Each one intersects at most n segments. So 2n plus 1 times n is also a constant times n squared. Okay, so that's the space. And how long does it take to construct one of these things? Well, that's not too difficult. In fact, all of the work that you do in the construction, right? One of the things is this plane sweep to figure out what your strips are. To do that, all you have to do is sort the endpoints of your line segments by x coordinate. So that can be done in n log n time using your favorite sorting algorithm. Since we've been talking about treaps, you might as well use quicksort as your sorting algorithm. That part is easy. And then there is the basically in each of these segments, you want a sorted collection of, in each of these strips, you want a sorted collection of the segments that intersect it. Well, that's also not hard. So initially in S0, you know there's nothing in that collection. In S1, well, S1 started, I mean, the reason you go from S0 to S1 is because you encountered an endpoint here, which means that in S1, the thing that crosses it is actually the segment whose endpoint you just encountered. And more generally, if I already know what's intersecting some strip like this strip S3, then the next strip over differs by exactly 1 segment. Either the next strip begins a new segment, in which case there's one more segment that intersects S4 in this example than there does S3. If we already have the elements of S3 sorted, well, then finding where this fits into that you can do in log n time, and store it in the right structure, and you can also insert it. Or sometimes you leave a strip, and what happens is that's because you're passing over the right endpoint of a segment, in which case you just have to take it out of the sorted list here. So actually, in a sense, the construction time, I mean, it can't run in n log n time because it sometimes has to build something of size n squared. But really, what's taking so long in the building is not any of this plane sweep stuff. It's not even getting the sorted lists. All that can be done in n log n time. It's just that when I go from strip I to strip I plus 1, I basically take a snapshot of whatever data structure I'm using to keep these things in sorted order. I have to save it because later on for queries, I need it to answer queries in that strip. So that's where the expensive work comes in. So really you could say the construction time, if you wanted to be more specific, it's like O of n log n plus the space that you need, right? Plus however many of these arrays you create. So sometimes that could be n squared, but the rest of the work is really just n log n. Okay. Now I think that already highlights, well, the real problem and the real bottleneck with this approach. It's not organizing the data in the right way. It's not finding all of the bits of the data structure that you need. You can create, one at a time these sorted things, but somehow it's just remembering what's in all of these strips. And there's something a little bit silly about the way we're doing it here, which is, I'm saying, well, once you've got your sorted array or sorted list or binary search tree that contains the elements that intersect Si, when you move to Si plus 1, all that happens is either one thing leaves or one thing enters. But you're going to create a whole new list, which seems a little bit crazy. Right? If the difference between what's in Si and what's in Si plus 1 is only one insertion or deletion, it seems completely silly to save everything in Si or copy it into Si plus 1 and then add the new thing. I mean, those two things only differ by one segment. So we would like to take advantage of that. So actually, I think what we want is, well, this is the problem we solve within a strip is just binary search. It's the thing that binary search trees solve. So what we would like is a binary search tree that remembers what happened to it over time. So as it changes, indeed, I can add and remove things, but you'd like to be able to go back to old versions and search in those old versions. So just imagine, here you have an empty search tree T0. Here for strip 1, you have a search tree T1 with one strip in it. This one has 2, this one has 3, and so on, all the way till the end, you get to T2n. So these are supposed to be binary search trees, one for each strip. Each one stores exactly the things that cross that strip. And you can build all these binary search trees in n log n time. That's just the plain sweep, and each one is an insertion or deletion. So you had them all while you were doing this, but you need to remember them. So that's this notion of persistence, is you take a data structure, like a binary search tree, that changes over time, and you ask the data structure to remember all of its previous states so that you can go back and search in those things later. And all I've said so far is, well, one way to do this is, before you go from Ti to Ti plus 1, copy everything in Ti and then make the change work on the copied thing and make the change, and then copy everything in that and then make the next change. Seems silly. There must be a better way. All right. And of course, I wouldn't be talking about it if there weren't a better way. So the first technique that gives a better solution than this n squared is also it's a technique that's kind of general, but each time you use it, you have to sort of check the details of what data structure you want to apply it to. So we will stick with a treap for now, because that's the binary search tree that we looked at. So remember, a treap is just a binary search tree. I'll draw it like a triangle. It has a root, and you can add or remove things from it. So, and you may or may not remember that when you add something, the way that that works is you search for it until you fall out of the tree. You don't find it because it's not there, but you fall out of the tree, so that means you leave the tree as the left or right child of some node that's in there. Then you put the newly inserted node in there. So you followed some path down. Finally, here's where you should insert the new thing, at least to get it in the right place in terms of sorted order in the tree. But remember, treeps have priorities, so this might not be in the right place in terms of priorities. So you do rotations to move it up the tree if necessary. Okay. And what I want you to notice is, or remember, each of those rotations takes this thing and just moves it up, moves it one step higher along this existing path. So suppose I do the following. So let's focus on this path here. Okay, so each node along this path has a child that is in the path, except the last one. And it has another child or a null pointer to something that's not in the path. So let's draw the other ones as well. Maybe something like that. And even the root has that. So there you go. So before I do this insertion, and this is going to be confusing, I take these things, these nodes, and I copy them. Hope I got the right number at least. Okay, so what does that mean to copy them? So I make a copy of the data that's in that node, and so on. I also want to copy the pointers, but being a little bit careful. One of the children of this node is in the path that I'm following. The other one is not. So the one that's in the path, I'm going to make a copy of it. So that's what I should point to. The one that's not in the path, I'm not making a copy of it. So I should point back to that one. So this is where it gets confusing, but what I would like you to do now is put your blinders on and imagine you're a computer. I mean, to a computer, what is a binary search tree? It's a pointer to the root. The way you access the binary search tree is you start at the root and you follow some pointers there around from there. So as the computer, if I give you a pointer to this thing, or I give you a pointer to this thing, you can't tell the difference. It looks exactly like the same binary search tree. Now, if I give you a pointer to this thing and say, okay, now do the insertion, add this new element. Well, you follow the search path for it. There it is. You attach the new element as a leaf, and then you do some rotations to bring it up. Those rotations only affect the nodes on this path. So after I've done that, starting from here, I have I see, what I see is a binary search tree that contains the new node. On the other hand, if I start from here, what I see is a binary search tree that doesn't contain the new node. It's exactly this one is completely unchanged. The only stuff that changed were nodes along this path. Okay. So if this is my tree Ti, then in some sense, Ti plus 1, I can get just by copying this path and now saying, well, when you want to access Ti plus 1, start here. This is the root of Ti plus 1. This is the root of Ti. Okay. Good. That sounds good. What about deletion? Well, I'll wave my hands a little bit there and say, well, remember that deletion and insertion are, one is just an exact reversal of the other. So in particular, when you want to do a deletion, it looks a little bit uglier than this. You can identify the path of all the vertices that will be touched by that deletion. And you first copy those. That gives you a new root. You do the deletion in that thing, and you get a fresh tree. If you don't believe me, if you don't believe that, then you can also think of doing it on the fly, right? When you run the deletion algorithm, you find the thing you want to delete, and you're going to rotate it down. Well, first finding it, you just search for it until you find it, and then you see that, well, the rotations down, they're constantly choosing one of the two children to swap places with. Well, that's the child that needs to be copied before you change it. So something is going to happen to that child, but that's the only thing. And then you repeat that all the way down. Okay. All right. So that's path copying. That's how you implement it for a treap. All right. So that doesn't really look like it slows things down considerably, right? I mean, to do an insertion, we had to cross this path. Now we have to cross it and copy all its values. But I mean, these are constant size nodes. Copying each one takes constant time. So the time to add something is only going to be same as before, O of log n, just with a larger constant. And the same thing happens with removing. Okay. So the running times stay the same. Each one is O of log n. The only difference is each of those operations now copies log n things. Okay. So we're golden. So this was the first approach. Second approach is, well, instead of having completely separate data structures for each strip, we just maintain one of these persistent treeps, and for each strip, all we need to do is keep the pointer to the root of the treep that corresponds to that strip. Okay, so we're going to end up doing n operations. Each one takes log n time, or it's 2n plus 1 operations, or 2n operations. Each one takes log n time. So that's going to be O of n log n time to construct it. The space is going to be O of n log n, because each time we do one of these operations, we're copying a whole path of length log n. And the query time is going to be O of log n, because again, the roots of these things will be stored in a, let's say, a sorted array. They're sorted by x coordinate because each one corresponds to a vertical strip. When we need to do a query, we search by the x coordinate of our point until we find the tree that we should be using, and then we just do a search in that tree. The binary search in the array takes O of log n time, and then searching in that tree takes O of log n time. So a dramatic savings in space, and well, of course, also construction time, because using that much space takes a long time. But I'm still not fully satisfied. This was too easy. And well, what else could I hope for? Well, I'm not that happy about this space usage here. You gave me n line segments, and now suddenly I'm using n log n space. It would be nice to just use a linear amount of space. The construction time, I can't really do much better than that, unless I want to do some assume something about the endpoints of my line segments, about them being maybe small integers, having small integer x coordinates or something that I could sort faster than general things. But so far, everything that I've talked about here just involves comparisons, binary comparisons of either checking if the x coordinate of your point is bigger than or less than some value, or checking whether the point is above or below some line. And we can't do better than n log n for the construction time if that's all we're going to do. And the same thing with the query time. Okay. But I would like to bring this down to linear. Now, how are we going to do that, or why should that even be possible? Well, one of the sort of finer points about treaps that I mentioned is the following. When I do an insertion in a treap, so I go and I find the place to add the new node, I attach it as a leaf, and then I said, well, then you don't have to do more than log n rotations. But then later I said, well, actually, if you analyze this thing more carefully, on average, in expectation, you don't have to do more than 2 rotations. Okay. So what's happening here seems overly aggressive. I'm copying an entire path to do this, and the most likely outcome is then what's going to happen is I'll do 2 rotations, which will actually have modified just these last 2 nodes on the path. Okay. Now, why did I do that? Why can't I just copy the last 2 nodes? Well, the problem there is at the end of this process, I need sort of 2 different search trees. I need the tree without the value in it, and I need the tree with the value in it. When I copied the whole path, I got the second one for free because the root of this thing works for that, is what I need. But if I were only to copy the last 3 nodes or so, last few nodes along this path, well, okay, then what happens? How do I search in TI plus 1? Because this tree doesn't have any pointers into that tree, so that something goes wrong there. But if you just think of, in terms of the minimum stuff that I would have needed to copy, it should have only been a constant number of things. And it's somehow just the fact that, well, the stuff that I needed to mess around with was far from the root, and so I had to copy everything from the root to that stuff. And that's why this is called path copying. But there's definitely an inefficiency there. Yep. Yeah. So so a couple of things that I quickly gloss over. This is useful. So depending on how you implement a binary tree, you may have nodes that have pointers to their two children, but also a pointer back up to their parent. Okay. And so if you think about that a little bit, then, so when is this parent pointer used? Well, it's used, for example, when you're walking back up the path to do rotations. But also a rotation changes the parent pointer, not just of the two nodes that you're rotating, but actually the things adjacent to it. So, right, so if I do a rotation that's going to change this edge, well, actually the parent pointer is at the roots of these three things also changes. So one solution is, well, don't use parent pointers because they were only really used for this walking back up the path, but you're already copying the whole path anyway, which makes it easy to walk back up. I mean, copy it into a, just store those nodes in an array just while you do the insertion. Then you don't need the parent pointers to walk back up and do this insertion. But another slightly more subtle thing is the parent pointers are only used when you want to change things, when you wanted to do rotations. And that really means that the parent pointers, and in what we're doing here, the only tree we change is the most recently created tree. So if you want to not change the algorithms very much at all for a treap, then these orange nodes here these ones that are the other children, they would have their parent pointers point to the newest copy of that node. And it's actually okay that they no longer point to here because you're never going to mess with this tree anymore. So that will also work. So there's two ways around it. Okay. But those are small details. All right. So now we'll go to something much more general than path copying. Basically something that lets you you can implement pretty much any pointer-based data structure. So data structure like binary trees or skip lists or whatever. Pick your favorite sort of pointer-based data structure. So I want to maintain a graph, and by graph I mean these things that we draw. They have nodes and edges. So it's actually going to be a directed graph, and it's going to be labeled so that there's labels on the vertices. So each vertex has a label associated with it that you can change if you want. So if you think about the data structures that you've looked at in the past, well, maybe you've seen skip lists, different kinds of binary search trees, linked lists, all these pointer-based things, they kind of look like this, right? You typically have some node, the node is storing some data, that's what I'll call a label, and the node also has some pointers to other nodes, and those are the directed edges that are in this graph. So this is a pointer from node A to node B, pointer from node B to node C, and so on. And I mean, just work your way back through the sort of pointer-based data structures you've seen, and you realize, yeah, they're all kind of like this. So a couple of operations that I want to do. Okay, so, and I should be a little more specific. I want these things to be highly structured. Again, just like most pointer-based data structures are. So these things have each node has, let's say, k outgoing edges. And they're numbered in slots. So, you know, for A, this is outgoing edge maybe number 1. For B, this is number 1, and this is number 2. For C, there's only, maybe this is number 2, and there is no number 1, but there's some fixed number of outgoing edges of each node. For instance, in binary trees, it can be 2 if you're only maintaining pointers to the children, or it might be 3 if you're also maintaining pointers to the parent. And indeed, there's special edges. There's a left pointer, there's a right pointer, and there's a parent pointer. Those aren't interchangeable. Okay, so that's sort of what the slots are supposed to mean. So I want to be able to make a new node, create a new sort of node with no edges or anything. I would like to be able to change the label on the node V, so to update it to whatever, some new label L. And I would also like to be able to change the edge coming out of V so that it points to W, and the edge that I want to change is edge in slot I. So for example, if I did a make node, that would create some new node. We could call it W. And if I say change edge W, let's say B2, then that would do something like this. And I could also say change edge maybe C2 or CW1, which would do something like this. Erase this edge and change it so that it points there. Okay. Those are the kinds of operations. It's really change the pointer coming out of a node, or change the data that's stored with the node if you change the label. All right, and I want this graph to be persistent. So each time I do one of these operations, I get a new graph. So initially I start out with an empty graph, G0. Then I do something. In fact, the only thing I can do is make a new node. That gives me a graph G1. Then I do something else. Maybe I could even make this thing only has one node, but I could change one of its pointers to point to itself, or create a new node. Whatever you want to do gives me a graph G2. And I do this for a long time. I get this whole sequence of graphs, and I would like to have access to any one of those graphs at any time. So imagine a treap where you use this interface to implement a treap and just do the normal treap operations, and what you'll get is, well, a whole sequence of trees where each one represents, the state of the treap at some point in the past. And the point is that a treap, when you do something like add, well, you should really only have to do a couple of these. You have to make a new node. You have to change one edge to make this node a child of something, and then maybe a few more edges to do the rotations. So the graph, that shouldn't change the graph by that much. Okay? And I would like all of this to be saved and stored in space that's just proportional to the number of these operations that I did. And the only condition that I'm going to need, and I'll write it up here, otherwise this isn't going to work, no node, or let's be more positive, each node has at most d incoming edges. Okay. So this is a important thing. This, unfortunately, in a few rare cases, this can limit what you can do. But again, probably most of the structures you guys have thought of, have seen, that's not a problem, right? Linked lists, each node, maybe if it's a doubly linked list, has 2 incoming edges. Binary search trees, each node has 1 parent, and if the children have pointers up, that makes 3 incoming edges. It's not a big problem, but there should be some, let's say, constant d that guarantees this. All right. So let's describe what this structure looks like. It's going to have nodes. What's a node going to look like? Well, what does a node need to have? It needs to have a label. And it needs to have edges, E1, E2, E3, up to EK. So that's a sort of important thing. And this, right, so that's sort of what you think it is. This stores the label. These are the pointers going out of it. And well, as you do operations, these things are going to change over time. So this won't just be one of these things. It's going to be a table of them. Okay. So each row of this table is going to have a timestamp that says this row was created, the data in this row was put in at this time because some operation happened that did that. Okay. And so we'll have a timestamp in each row of this, this table. Good. And well, if this is the way you're going, and you may be tempted to go this way, the first thing you would try is something called the fat node technique, which just says, well, this table just keeps getting bigger and bigger. Whenever you change a node, this thing gets bigger and bigger and bigger. So that's not going to be what we do, and it's not a great idea because that means that if I just let this thing get bigger and bigger and bigger, then that means at some point I will want to access this node at some point in time. And well, the only way to do that is to find the right row for that point in time. But if the table is arbitrarily large, that's at least a binary search, and you won't be able to access it in constant time. We would like to be able to access the version we want in constant time. So we'll only allow d+1 rows in this table. If it fills up, we'll have to do something else. Okay, and then off to the side, we have a little list of d other nodes, each of which has an incoming edge to this node, right? So for instance, D over here in its list of other nodes would be B, just to remind it, because this will be important at some point, that, well, there's an edge coming into me from B. It's not part of the graph, but for making this data structure work, we're going to have to keep track of this. Yeah. Well, if the problem is anybody can come along and change a label or change an edge on a vertex as often as they want. And if they do that, then the number of rows will get really, really big. And then finding the row that I want will take too long. So we'll fix it so that that doesn't happen. Okay. All right. So and the thing to sort of keep in mind is each of these things, each time you do one of these operations, time advances by 1. So we're always, each time this happens, we keep track of, okay, first operation, second operation, and so on. Yes? Yeah, it's the maximum number of incoming edges. Yeah, 3 rows. Yeah. Every node will have at least one such table. Okay. All right, so let's see how we do these operations. Make node. Well, I think that's kind of easy. We make a table. Okay. So it's asking us to create a new node that doesn't exist yet, so we make a table. Nothing terribly interesting happens, except we fill in the first row of that table with the current time, and the label is null, and all the other edges coming out of it are null. But it's there, the node exists. If you ask me about it at right now, if you ask me about it for any time value bigger than or equal to t, I can tell you this is what it looked like. That's easy. Okay, how about change edge? I think that's kind of easy. So we can do an example. Let's say this is the node, this is the table for node V, and we would like to take EI and have it point to W. So we look at the table for V. It has some rows that are filled. If we get lucky, there's one that's they're not all full yet, in which case we take the current time, whatever that is, we mark that as the time for this, that this row becomes active. We copy everything else from the previous row, except for EI, we change that thing so that now it points to W. So that is the table for W. Okay. Easy enough? Yep. Good. So that's change edge, except sometimes we don't get lucky and we end up changing an edge on a table that looks like this. It's completely full. So now what do we do? No problem. We create a new table. Same size as the previous one. We take the last row of this table, copy its contents into the first row of the new table. So this is going to be the new version of V now. The timestamp, we put the current time here in the first row of this table. And we make the change to the edge. So one of these edges, EI, should have its should be changed to point to something else. Okay. All right. So far, so good. There's just one issue, though. There are other nodes, potentially many of them, that point to this node, right? If this is V in our graph, there can be other nodes like X, Y, and Z that point to V. Currently, those nodes are pointing to this table, but we're about to be done with this table. This is gonna become the new table for V. We need to tell those nodes that they need to update their pointers. Okay. So we go through this list of, remember we've kept on the side this list of nodes which have incoming edges to us, and we call change edge for each of those in order to update them, so that now instead of referring to this thing, they'll recursively call it on this node, so now it will refer to the new table. So change edge on V can end up splitting this table and then having to call change edge up to D times on other nodes so that they update their pointers to point to this new table. Sounds terrifying. Sounds like this cannot possibly work, right? All right, good. Okay, is that everything clear-ish? Yeah. Well, so that's something you have to tell me in advance. You say, I want a persistent. So I tell when I build the data structure, I say, okay, I want a persistent graph, and I guarantee you that at no time will any node have in degree larger than D. And so, if you're using this to implement a data structure, usually you understand your data structure well enough to either say, that's easy, D is never more than 3 or 5 or whatever, or to say, I can't guarantee that, in which case you have to find some other solution. But, yeah.
What do we create a new table? Can we just keep an index module up and rewrite?
No, we don't want to rewrite any of these things because we always want to be able to go back to any point in past.
So we keep that one.
This table is still sitting off in memory somewhere. None of these other nodes refer to it anymore. Although remember, these other nodes, they're doing the same thing. So like this node up here, for instance, has one row with a pointer to this. Then when this table gets split, that creates a new row where that pointer changes to this thing.
So for each node, we have an array of tables.
It's not an array of tables. They're just floating off. There's nothing globally storing those things. I hope you have a good memory manager on your system, because it's there's a lot of stuff floating around. Okay, so that's how change edge works, and there's nothing different about change label except it's a little bit easier. I mean, it's the same thing, right? If you have space in your table, you just fill in a new row with the new label and the new timestamp, and if you don't have space, you split it and then fill in the first row of this new table, and then notify all the incoming edges that they need to update themselves as well. Yep. Yeah. No. So when I change from V to W, so that's what I did here, then yes, up here, this was pointing to something. I don't know what, but I don't need to tell them about that. I mean, if I want to be fussy, I can say, okay, I'm not in your list of incoming edges anymore. Maybe you can do that, but you could also, this guy could also figure that out in another way. I guess W should have his list of incoming things updated to point back to V. But these things are not persistent. They're just for the current, what's happening right now. Okay. All right. So if you've been following, you should be getting worried now that there's no way this can work. And the reason that this kind of thing should worry you is nothing says that I can't have a graph like this. And what I said is, if I decide to change something, even just the label inside this node, so I don't even change the graph at all, I just change the label, then, well, this node is actually a table. And sometimes that table gets full. And when the table gets full, you split it. And when you split it, you have to notify all of the nodes that have an incoming edge to it that they need to update themselves. So this guy needs to update to point to there. But this is the same kind of node. It's got a table. And maybe that table is full. So in order to update it, it needs to create a new table. And well, the same problem. Now this one gets notified and looks like it can go around in circles. Okay. Looks worrisome, but it actually doesn't happen. And we're about to see why. Okay. What's that? Yes, yeah. When we do this recursion, each one of these gets a new row with the current time marked on that new row. Yeah, maybe, but that's not the clue to stop. Here, for example, I think you can maybe see why this doesn't go around forever and ever, and I'll tell you why. This graph, it's just a cycle. The max in degree is 1. So that means these tables have 2 rows. So this one was filled. We tried to change the label. That created a new table. That filled the first row. And then this needed updating. And then maybe that split this thing. And maybe that split this thing. Maybe that split this thing. And now suddenly this needs updating. But now we're okay. Why are we okay? This new table has an empty row still. So the process will stop right there. And now, pay attention. That's why this number is d+1 and not something less than d+1. So all we need to do is make sure that all of this works. So we're going to use what's called a credit scheme. So 1 credit pays for 1 table. So each time I create a new table, I'm going to pay for that with a credit. Good. And each call to make node comes with 2 credits. So when the user says, I want to make a new node, the user has to give me 2 credits. So one of those is going to have to be immediately used to pay for the table that I'm creating to make that node. The other one I can put aside, save it for later. And each call to change edge or change label comes with 1 credit. Okay. So when the user says, I want to change the label on some node, they have to give me a credit to pay for that. Most of the time, I won't need that credit right away. I'll save it. But sometimes I'll have to spend those credits. And I want to be clear, that's only when the user of this data structure asks me to change a label or to change an edge. Internally, I may call change edge. That's what happens when you split a node. Some things need their edges changed. In that case, I have to provide the credit from the ones I have saved to give to change edge, to pass that in. Okay. And the way we're going to make all of this work is to maintain the following invariant, which is that each row of each active table stores 1 credit. So it has 1 credit saved up. So just to sort of be clear, when a table is full or partially full, it's an active table. It's the current table for this node now. But once I split it, so once it becomes overfull and I have to make a new table, this becomes the active table, and this one is inactive. Okay. So these active tables, if there's this many rows filled in, then I should have the same number of credits stored alongside that table. The inactive tables, I don't guarantee anything. They're done. They don't store anything. All right, so let's see if we can maintain this invariant and at the same time pay for each table that we create. So make node creates a new table. So it comes with 2 credits. The user gives us 2 credits. One of them we immediately pay to make this new table. So that makes sure that we're never going to make more tables. By doing this, we're sure we're never going to make more tables than the credits we were given, which is the number of these, twice the number of make node operations and once the number of these things. So 1 credit goes to create that table, gone right away. That table has its first row filled in, right? Everything is null, but there's a timestamp there. That's the state of that node at that time. It's an active table, so that extra credit that we were given, we put it there to maintain the credit invariant. Good? I'm not trying to trick you. This is all above board. All right, so that we can deal with make node, no problem. And the table that got created, we paid for. Let's look at change edge. Well, change edge, there's sort of 2 cases, right? There's the easy case and the hard case. The easy case is you have a table like this that still has 1 or more empty rows in it. And you come along and you say, okay, I want you to change one of the edges. So you copy everything from the previous row, change the appropriate thing to do whatever, set the timestamp to the current time, and the caller of change edge gave you a credit, which you don't need to spend right now because you didn't have to create a new table. But you need to save it because the credit invariant says you need to have a credit on every row of every active table. This is an active table. I just filled in a new row. So that credit that was given to me, that's where I have to put it. That's the easy case. Then there's the hard case, which is when the table is already full. And I have to split it. So let's see what we've got here. This table is full. Somebody asked me to change an edge. So when they asked me to change the edge, they gave me a credit. This table is active and full. That means it has D plus 1 credits sitting on it. Every row has a credit on it. So in total, I have D plus 2 credits to play with. And I'm going to need them. Okay, so let's see. Well, we're going to create a new table. When we split this thing, we create a new table. We have to pay for that. We promised that we would pay for every table we create, so we use one of our credits. One pays for new table. But wait, that new table we just created is active. This one is inactive, which is good. That's why we get to wipe off these credits and start spending them now. This is active, and it has a first row with some values in it. We copied them from the last row of this table and then changed one of them. The credit invariant says we need to have a credit there. That's 1 to maintain the credit invariant. Wait, that's only 2 credits. We paid for the table, we maintain the credit invariant. Do we win? Do we just make D dollars? Yeah. We still have D, we only spent 2 credits. We still have D left from all the ones that we had in our hand. But remember, the last thing we have to do is tell the D incoming nodes that have incoming edges that they need to change one of their, each one of them needs to change one of their edges to this new thing. And that is a call to change edge, which is not coming from the user. The user gives us a credit each time they call it. We're calling this ourselves internally. We have to provide the credits. But there's only going to be D calls to those things. And we have, well, D credits left. We spent 2, we had D plus 2. We have the D that we need to put into those things. Okay. So, and then we use 1 credit each for each call to recursive call to change edge. Okay. And that's it. If the user makes n calls to make node, that means they gave us 2 n credits. Then if they do m calls to change edge or change label, they gave us an additional m credits. In total, we pay for everything that we make, therefore we never make more than 2n plus m tables. And these tables, they're of constant size if D is a constant and K is a constant. So think of all the data structures that you're thinking of. And that's really the only work that we do in any of this stuff is making these tables. So really this tells us how long this sequence of operations is going to take. Something like the number of make nodes plus the number of change edge, change label. So on average, each one of these operations takes constant time. All right, so so there you go, persistent dynamic graphs. So I guess I should mention the last thing. How do you navigate in one of these things? Well, if you're at a node you're interested in some point in time, t, and you're at a node that has a row for time t. So that means that the time you're interested in is is bigger than or equal to this, but less than this, say. So this is the node you're looking at now. It's active at that time. It's what you were using. What do you ever do? Well, you look at the label here, maybe that's not a problem. Or you follow a pointer. You mean you follow one of these edges. So you follow one of these edges, and everything that we have done guarantees that wherever that points to is a table that has an entry which was active at the time you're currently interested in. Right? That's the whole point of this. This thing can only point to tables that have entries that are active at the current time that I'm interested in. So yeah, you'll have to search through these D rows, but that's only a constant number of things. And you find the right row, the one that has the time you need, and you keep going from there. So you can move from one node to the next in the past at any specific point in time using using this idea. Okay, and you have to stretch use your imagination a bit, but you can use this to implement a treap. And now in particular, to implement rotations in a treap. That's what changes stuff in a treap, really, and one pointer move when you do an addition. You can use this to implement a treap, and we said, well, the treeps, each insertion on average only does a constant number of rotations. Each deletion also on average only does a constant number of rotations. So I can do n operations on a treap, have access to every version of that treap over all those n operations, and the space is only O of n. And it's erased by now, but that gives a solution to the next element search / point location problem that uses linear space, n log n time to build, and log n time to answer queries. And it does a lot more than that. So the assignment has a couple of questions on it where you can think of how useful this persistence can be, even if you only apply it to things like binary search trees, the neat kinds of things you can do. Now that you can go back in time and look at old versions of the tree, any old version of the tree that you wanted. Yep. Okay, so first, I'll just say the class is officially over, so you can pack up and leave if you want, but I'll also take questions. Yep.
We don't actually end up doing a loop because we have an empty row. But that empty row actually gets filled in the last step.
Yep.
So, and then from that point on, we have to create a new table basically to maintain the changes after.
So if I change this again, then so you think, oh, now we have to do a whole cycle around this thing. So if I change this again, yep, I have to create a new table here. That has to update this one. But remember how we got here. We got here because this one just was split. It has an empty slot now. Yeah, so that would be bad. I mean, this loop can be arbitrarily long, and you really can do one operation that causes every table on the loop to split if you load things up just right. But then once you've done that, every one of them has a free slot in their table. So not going to happen again. In fact, if you do some careful counting, you'll realize basically this one only gets split 1 out of every 2 operations, this one 1 out of every 4, this one 1 out of every 8. And so if you just keep changing the same thing over and over. Okay, and you can also think a little bit here about there's a relation to what we did here and fractional cascading. And I think you can kind of see it. Fractional cascading, we said, if you have a string of elements, you should push every second one down, or every fifth one down, or every 10th one down. That's what's happening with these tables. We're basically saying, I have a string of changes that happened to this node, And every d plus 1th one, I want to push that information out to the other nodes that reference this one. It's just that this is happening in a much less structured way. And so it takes a bit more care to analyze. All right, so now I'm really done. Please ask me questions if you want, but feel free to leave. Well, the actual space is 2n times, I mean, k pointers times one label times d plus 1. I mean, there's a lot of constants in there. So, I mean, it's if all of these parameters are constant, k and d and whatever, I can say the space is linear. It's O of n, but it depends on what those constants are. Yeah.
So each pointer points to a table, right?
Each pointer points to a table. Yeah.
So you're keeping a log of all pages. But what if, what's the point of the log? If one of the pointers is pointing to valid table?
No. So the last row in an active table is always pointing, is only pointing to other active tables.
So like, what's the point of keeping track of the previous log?
Oh, because at some point I'll want to go back way back in time into inactive tables, right? Because those are just nodes from my, let's say, my treap from a long time ago that I still want to use and search in, and I can use those, and those will take me to probably to some other inactive tables, but that have the data from back then, from that point in time. So you remember everything for forever. Yep. Let me stop recording.